now, right? Okay, about kinetics, what it is about, what is the aim and scope of chemical kinetics? Well, it's a very important subject, central to everything in chemistry. It roughly deals with chemical reactions and how fast and how they occur. So they're very much about reaction rates and reaction mechanisms. Now, of course, kinetics is also important in many other areas, not necessarily with chemistry, but also in more applied sciences like food, in the food industry. For example, if you deal with the issue of food spoilage, you may want to know why a certain product, perishable product, spoils faster than others. What is the mechanism of that process? Once you understand that, you know at which point you should intervene and what should be the nature of the intervention. So what are the mechanisms of these bad reactions? What is, well, in medical sciences, kinetics plays an important role. There is actually a field in medicine that is known as pharmacological kinetics that deals specifically with the question of how pharmaceuticals act within the body, how they distribute themselves through the bloodstream and through the lymphatic system, or how they permeate cell membranes, those type of questions. Biochemistry is another major area. Biological sciences generally, where we study metabolic cycles in living organisms. And in particular, we study reactions that are facilitated by enzymes. All the life-sustaining processes are catalyzed by enzymes, and their mode of action can vary widely. So an important aspect there is the kinetics of mechanisms that will give you a grasp of what is happening and how fast it is happening. We will come to discuss one of those mechanisms further down in the course. You notice the slides that are brought up are all PDFs. That is how this platform works. Any PowerPoint presentation automatically convert to PDF, so you only get these still images. So you lose the option of having animations that you have on the PowerPoint. But the PowerPoint slides are online. I've posted those, the first one already on our VLE site. Okay, another area of application I would like to mention is in atmospheric chemistry. In particular, the study of the kinetics of processes in the upper atmosphere, which some years ago has led to an insight about the rather damaging action of certain products, so-called CFCs, chlorofluorocarbons, which were found in propellants and refrigerants, for example. And they have now been banned worldwide because it was discovered that they had this bad effect on atmospheric ozone. And well, these substances have been gradually replaced with other compounds, the so-called hydrofluorocarbons, which are environmentally more benign. Other important applications of kinetics are in the study of, okay, there is a query here from Michelle Ashley. Let me see what.
Sir?
Yeah. Okay.
Are you switching slides? Are you
Sorry?
Are you looking off some slides, sir?
Slides. Yeah, you can see the slides. They're up.
No, sir. We can only see the first page.
Right. You won't see. Yeah. Okay. But I will bring up the next one. Okay. You see the next one now?
Yes, sir.
Okay, right. So
Cause
I
you
will
weren't seeing
advance.
anything. Just heard you speaking, but I wasn't sure where you were.
Okay, no, the slides should be visible to you. So I will advance them as we go along. All right.
Okay.
Right. Good. Okay. Another important application is in the field of corrosion protection and corrosion control. Um, so I'm still doing introduction, right? So we in corrosion studies, well, that's a worthwhile undertaking because corrosion damages can be extremely costly. It has been estimated that a couple of percent of 2 to 3% of the GDP of, at least in the industrialized nations, is spent on maintaining and replacing large infrastructure, metallic infrastructure like bridges, railways, uh, what is oil rigs, those things. So, and that is due to corrosive damage that is done to them. So, to prevent that damage and to control it, the process, a thorough understanding is required of the mechanisms of corrosion reactions. So that is a very important field of application there. Yeah. All right, now let me bring up the next slide. So here's some general info. So Tuesday 5, that is now the my office hour. So make sure you avail yourself of the option. So every Tuesday at 5, you can come back to this BBC platform and with prepared questions, and I will address the best of my ability. And Wednesday at 9, that is the regular lecture slot now, right? These names are from persons, colleagues who taught this course previously. I'm not sure if this is still the format, but I will have to check with the coordinator, Dr. Stevenson. Okay, let's move ahead now. So as I told you, the chemical kinetics is all about the rate of chemical reactions, but also, even more so, the mechanisms of those processes. Now, what determines the rate of a chemical reaction? Now, obviously, what are the reactants and what are the products? That is the first thing, the ingredients of the process. Temperature is always a factor, and typically, whenever you increase the temperature, well, a reaction tends to speed up. Okay, there's another query here. Michelle Ashley, you can go ahead. You want to say something? Or you forgot to lower that? Okay. Well, temperature, obviously. The presence of catalysts. I already mentioned the biocatalysts, the enzymes, and their importance in sustaining life processes. Catalysts who themselves are not converted in a reaction, but facilitate and speed up the process. Concentrations, of course, are important. Increasing the concentration of one of the reactants normally speeds up the process, but it could also slow it down. Some compounds can act as inhibitors of a process. So if you increase the amount of them, it will slow down the process. Yeah. Another point which was missed here, I think, is the influence of light, sunlight in particular. There's a large class of reactions that require light, electromagnetic radiation, to start and to proceed. The most important reaction actually is the photosynthesis reaction in green plants. Right? So that is triggered by sunlight and sets off a chain that in which water and carbon dioxide are used and converted into hydrocarbons, which is basically the bottom of the food chain that you're looking at. So photochemistry is extremely important. So light-induced reactions. No? Okay, now broadly speaking, there are two types of reactions. There are what you call the homogeneous reactions, which are those that occur, that take place in the bulk of a phase, in a gas or in a solution. So a gas phase reaction is shown here. So the formation of hydrogen iodide from hydrogen and iodine gas, right? Or liquid phase reactions, which typically involve ionic species. So an acid-base reaction, neutralization, right? Then the other class of reaction are the heterogeneous reactions. Those are the reactions that occur at the boundary between two bulk phases, and these are very common, very numerous. I've already shown you this, this reaction here, which is the oxidation of iron by an acid, which is an example of corrosion. Now, corrosion reactions are basically heterogeneous processes. All these reactions may be either very fast or very slow. We know that, well, you can have explosive reactions like combustion processes, or combustion of hydrocarbons. Other reactions are very slow, like corrosion, which is also an electron transfer process, a redox process. And kinetics is basically the study of the rates of these reactions, yeah, and their mechanisms. Another important heterogeneous reaction is the one in used in the food industry. It's a catalytic process. Well, many catalytic processes occur at the interfaces of solids, like nickel surfaces, or platinum. That is the reaction that saturates unsaturated compounds, like fatty acids. Yeah, these are the hydrogenation reactions, which do not normally occur in the gas phase, but if the reaction proceeds on the surface of, say, nickel, then it goes fast. So the substrate then acts as a catalyst. What happened now? In a way, the subject of kinetics is complementary to the other topic that you have just completed in the 1902 course, which is thermodynamics. Now, as you know, classical thermodynamics is essentially dealing with the structure and composition of equilibrium states. You know? It's all about equilibria, chemical equilibria, or physical-chemical equilibrium, phase equilibrium, that kind of thing. Kinetics, on the other hand, is dealing with the approach to equilibrium in a very broad sense. So what kinetics does is to find out how and how fast an equilibrium is attained. Also, because of that, kinetics will also make a prediction about how an equilibrium state, what an equilibrium state looks like. And that imposes an important restriction on kinetics, because that prediction will have to be consistent with the thermodynamic prediction. If it doesn't, then you will have to revise your kinetic model, right? So that's an important reference, thermodynamics. So keep that in the back of your mind. Now, all these factors that were listed earlier, including light, will affect the composition of a reaction mixture as time progresses, right? As the system, well, approaches equilibrium. So increasing the concentration, for example, will speed up the reaction. Now, to quantify the process, we need to have something like a measure of the rate of the reaction. Now, it's a bit problematic because in the course of a process, that rate will vary, because as a result of the reaction, the composition of the reaction mixture will change continuously, and it will therefore affect the rate of the process. So that is the reason behind defining reaction rate, instantaneous reaction rate, as a differential quantity, in the same sense that we have to define the speed of an object that is freely falling under gravity. You know, under free fall, the speed, an object picks up speed. So you cannot say the speed during the fall was this or that. You can only say at this point, while the object was falling, it had this or that speed. So it started in rest, speed 0, and as it touched the floor, it had picked up well, X amount of speed. But speed is then, at a given instant, is defined as the rate of change of position. Yeah? So if you follow the object for a very short, say infinitesimal time dt, it is displayed by, well, through a distance dx. So dx divided by dt then defines the instantaneous velocity or speed of the object. Now, it's in a similar way that we define the rate or speed of a chemical process. And the definition is variable because you can formulate it in terms of a rate of change in the amount or concentration of any of the reactants or products. Yeah, so reactants are being used up. Yeah, so the change is negative for them. For the products, it's a positive change. Yeah? So one possible definition focuses on the time course of the concentration of compound A, one of the reactants. So we could define the rate of a reaction, which we require to be a positive quantity, as the negative of the change in the concentration of A during a short time interval dt. Yeah? And then we take the limit of dt approaching 0. So dA is negative, yeah, because it is consumed during the process. So we put a minus in front to ensure that R will be positive. Well, that is not an entirely unambiguous definition, because the rate at which compound A disappears may not necessarily be equal to the rate at which B disappears. It is only if the stoichiometry of the reaction is such that at each reaction event the same number of A's disappear as B's. So if A is 1, lowercase a is 1 and lowercase b is 1, for example. But if A is 1 and B is 2, for example, then in each reaction event you lose 2 B's and 1 A. That means the rate of loss of B will be twice that of A. Right? So if A is 1 and you define the rate as negative dA by dt, in order to get the same value for R, if you focus on the rate of loss of B, you would have to halve the rate, that absolute rate of loss of B. Right? You have to divide by 2 to compensate for the fact that B is lost twice as fast as A. And more generally, the practice is that you define the reaction rate by the rate of loss of a reactant, in an absolute sense, divided by the stoichiometric coefficient with which that compound occurs in the reaction equation. So then you can never go wrong. You will always get the same outcome. And okay, so the question is, if I could go over this again, right? So suppose A is 1 and B is 2. So you have A plus 2B reacting, right? So when one reaction occurs, an elementary reaction occurs, you lose 1A and 2 B's at the same time. That means the rate of loss of B is twice the rate of loss of A. That means that the dB by dt, the change in concentration B in unit time, in 1 second, say, will be twice that of A. So in order to have the rate as defined as negative dA by dt equal to this, the rate of loss of B, we have to multiply this by a half, right? to cancel out the factor of 2. And the same by extension applies to, you got it? Good. And the same can be generalized to product C and D. There, of course, you use the plus sign because the concentrations of C and D go up in the course of time. So here you can retain the plus signs. Yeah, so that is the definition of reaction rate. The D's here, there's a question about that. The D's represent, you could delta, you could call it delta, right? But a very small delta, right? It is, a D always represents a change. So this is the change in concentration of B divided by the change in time during which that change in B occurred. And if you make dt very small, you could initially write it as delta B over delta T. If you let the delta T go to 0, then you write it as dt to indicate that we are considering an infinitesimal time. Good. Now, there's a caveat here, which it's not written on the slide, but this definition of reaction rate does implicitly assume that if A and B react in this particular way, then at the same time, simultaneously, C molecules C and D molecules of D will pop up in the mixture, which is not necessarily the case. The reason is that most reactions occur via a mechanism, means A and B do not react directly in a one-shot fashion to produce the products, but rather the reaction will proceed through a series of intermediate steps in which intermediate products are being formed, which are typically free radicals, right? And these then proceed further and eventually produce C and D. So the reaction mixture, it would be an oversimplification to consider the reaction mixture as consisting solely of molecules A, B, C, and D. Also, all the intermediates that are involved in the mechanism of the process will be present at definite concentrations and actually will remain there even as the reaction approaches equilibrium and reaches equilibrium. So that is a rather subtle point that is not evident from this slide. Okay, move on now. So here's another example of how to go about defining reaction rate. This is the reaction between hydrogen and oxygen in the gas phase producing water, right? The reaction ratio, so the stoichiometric ratio of hydrogen to oxygen is 2:1. So according to the general definition, we would then write the reaction rate in terms of the rate of loss of hydrogen, the change in concentration of hydrogen with time, multiplied by 1/2, which will be equal to the rate of loss of oxygen, or the decrease in oxygen concentration with time, right? Because hydrogen is consumed twice as fast in the process as oxygen. So the dH2 by dt is twice the dO2 by dt. So if you multiply both by 1/2, then it becomes an identity. That we define as the reaction rate, which alternatively we could define in terms of the rate of formation of water. So the rate of change of concentration of water in the gas phase. And you multiply that by 1/2 because of in each reaction each event, 2 molecules of water are being formed. Now, in terms of units, the rate of a reaction always is given the same unit because it is given as a rate of change of concentration. Concentration is in moles per liter, and time is in seconds or minutes, doesn't matter. But a rate of a reaction is always given in units of concentration upon time. So that could be mole per liter per second. Okay, now if we were to monitor the concentrations of these reactants over time, so A is a reactant and C is a product, you will see there's a steady decrease in the concentration of A and an concurrent. Okay, what was the question again? Trying to look at the chat, the questions in the chat room, but there was a question about endothermicity of reactions. What was that question? Because it's no longer on the screen. Of course, the matter of endothermicity or exothermicity, which is of a thermodynamic nature, is not really that significant in a kinetic context. You know? The reactions are spontaneous or they are not, and they are spontaneous. Okay, if they were exothermic, would the plus sign on the right hand side? Oh no, the sign has nothing to do with the thermal aspects or the calorimetric aspects of the reactions, right? The minus and plus are just there to ensure that the rate of a reaction is always a positive quantity. Yeah? Well, the spontaneity of the process, of course, is governed ultimately by the second law of thermodynamics. That the process will have to be accompanied by an increase in the entropy of the system and that of its surroundings at the same time. Otherwise, it won't happen. Okay? Right. So, so this is just an example of the time trace of the reactant A, concentration of A, and that of the product C. At a particular time here, the rate of the reaction, which is defined as a differential quotient, dA, change in A, during a short time interval, dt, can be interpreted as the gradient of the tangent to this curve at that time. Yeah? So the curve can be approximated during a very short time interval by a straight line, which coincides with that tangent. So the rate of change of A will be the rise or drop, in this case, upon the run, right? Which is the gradient or the slope of that tangent. And likewise, well, assuming that A occurs with stoichiometric coefficient 1. If it is 2, then you would have to halve this value, right, according to the definition of reaction rates. The C, the product C, there you would define reaction rate in terms of the gradient of the tangent, the slope of the tangent to the curve at that time, T. Yeah, so dC by dt. So that is the geometric interpretation of the reaction rate, the instantaneous reaction rate at a particular time. And you see that eventually the rate will go to 0 as the curves level off and an equilibrium is established. Good. Now to quantify the effects of, in particular, concentration upon reaction rates, we'll deal with the effect of temperature later on, which can be treated in a more unified manner. But our first focus will be on the effects of reactant concentrations upon those reaction rates as defined earlier. Now, those instantaneous reaction rates can always be formulated mathematically in terms of the instantaneous concentrations of the reacting species in the mixture or other species that might be involved in the process. So the rate of a reaction, as defined previously, is always a function of the momentary composition of the reaction mixture, and more specifically the concentrations at a given time of those reacting species. And very often, the mathematical form of that dependence looks like this, looks like what we call a monomial. So it is proportional to the concentration of A raised to an index m, and m may be 1 or 2. It could even be 1/2 if you see a fractional index. It usually means that, well, f is just a generic symbol for a function. So f is a function of A and B concentrations. And one particular instance is shown over here, where the function is a proportionality of power of A to the power m, and B to the power n, where m and n are either integers or fractions. In the case of a fraction, you know that the reaction must proceed through a complex mechanism, which you are then expected to unravel. But in the first instance, you would get from experimentation values of m and n. You cannot predict it, right? Because these reactions are usually way too complicated to make any theoretical predictions about them. You always have to do experiments to find out. Okay, the remaining factor in this rate, in this function, is independent of those concentrations, but can depend on other factors, in particular the temperature. And we lump all these dependencies in a factor that we call k. We call that the rate constant, even though it is not a real constant because it varies with temperature in general, right? So the rate law can then be formulated thus. So the rate is defined as the rate of loss of compound A, possibly multiplied by 1 over the stoichiometric coefficient, equals that rate constant times concentration of A to the m times concentration of B to the n. Now, if it is a bimolecular reaction. So this mathematical expression here is called a rate law. And it is a purely mathematical exercise to solve that equation, if it can be solved, to find an expression for A and B explicitly as functions of time. So in other words, to make a prediction of what these curves will look like, which you can then proceed to verify experimentally. Yeah, so that is the mathematical framework that is used for kinetic studies. Well, it is not necessarily dA by dt. You could also formulate it in terms of the rate of change of B, of course, right? This is just a choice to write R as minus dA by dt. Now these exponents that we saw there, the indices m and n, are called the order of the reaction with respect to reactant A, that is m, and the order with respect to reactant B. These are just definitions, just names. And if the rate equation happens to be of that form, and that doesn't necessarily have to be the case, I mean, you may get, besides products, you may have A divided by B or A plus B. I mean, all of that can occur, right? Any algebraic form is possible, depending on what the mechanism is. And that will be the subject of study in a more advanced course of kinetics in year 2. Now, in the special case where both m and n are equal to 1, we have the reaction being first order both with respect to A and with respect to B. For a monomial form, as we are considering here, we can then define an order of the reaction as the sum of these indices, 2 in this example. Now, depending on the form of the rate law, the rate constant acquires a unit. Yeah? The reason being that reaction rate is always expressed as a concentration, moles per liter, per unit time, per second, say. And the same unit, the right-hand side must have the same unit for consistency. Now, depending on what M and N are, the product A to the M, B to the N will have a particular unit because both A and B are concentrations, right? In order to reach dimensional consistency, K must have the unit of reaction rate divided by the unit of concentration to the power n plus n. So the unit of the rate constant is variable. Depends on the particular rate law, right? So in this particular example, the unit of K is found by expressing K as the rate divided by the product of A and B, and then substituting for these symbols the respective units. So mole per liter second divided by mole per liter square. So the square here cancels the mole per liter there. And if you invert the mole per liter that remains in the denominator, you get liter per mole. So liter per mole per second will be the unit of the rate constant for a second order reaction, as we are considering here. If it is a first order reaction, which is also a very common instance, common case, so the rate is then given as R rate equals minus dA by dt equals K times A. So K is then the rate upon A, and then you see that the concentration unit cancels out, and we're left with reciprocal second as the unit for the rate constant in a first order reaction. Another notion that is just a matter of definition again, that is known as molecularity. Now, molecularity is basically the number of molecules that has to come together in order to effect a reaction. Whether it will happen or not is a second question, but of course there has to be enough energy present for the reaction to occur. But the first thing that is required is that we need to have a certain number of particular molecules coming together at one time in what we call an elementary step. The elementary steps are really the building blocks of the more complex reaction mechanisms. There's only a handful of different types that we have to consider and which form the subject of our short module here. The first one is when you have a so-called unimolecular reaction, which only involves a single molecule. That is so that's easy. So for example, this molecule here, cyclopropane, which is a fairly strained molecule, under the influence of thermal motion, it can shake itself into a different configuration, a propene molecule, and that reaction is virtually irreversible, right? So this is an example of an unimolecular process. The other type of reactions, elementary reactions, is where you need two molecules to come together at the same time. And you have two types, one in which you require two molecules of the same type to combine to form products, so-called homomolecular reactions, or heteromolecular reactions, where you have two different types of molecules coming together to form products. These are bimolecular processes. So like this iodomethane with acetate, and that forms this reaction, and a solution reaction here, right? So this is an example of an A plus B type reaction. Okay, there was a question there. Jordan?
Yes, sir. Morning.
Hi, morning.
Okay. For the bimolecular reaction, you're saying it could be two reactants of the same state, like the solid and solid.
Yeah, right.
Or it can be two different types of reactants, but they have to be in the same state.
Well, they will have to come together and form a complex to form the products. So it needs an encounter for the reaction to proceed, requires an encounter of either two A molecules or an A and a B molecule.
Oh, so you're just saying that they can be of the same type, then, like hydrogen and hydrogen, for instance, or
Yeah,
hydrogen and iodide.
Right, yeah.
Oh, okay, sir.
Or two, what I would specifically think of is two free atoms, yeah? So free radicals, like two atoms of hydrogen that combine into a molecule of hydrogen.
Okay, sir. All right, thanks.
Yeah? Okay. All right, and then the third type, which is rather rare, so we will not elaborate on that, which is a thermomolecular process, which requires a three-way encounter of molecules. So like two A's and a B, or an A, B, and C, those type of scenarios. But we will not elaborate on that because in most mechanisms, these play a very minor role. Most elementary steps in mechanisms are either unimolecular or bimolecular. So those we will focus on. Yeah. An important thing to keep in mind is that molecularity is not necessarily the same as the order of a reaction. It is only the case if the reaction is of an elementary type. So one of the two that we just highlighted. Important message here that the reaction order is determined by experiment only, because the complexity of actual reactions is way too great to be handled by even the most powerful computers. So kinetics is very much an experimental science, and there's a wide range of techniques and methods available to us to study these processes in a systematic way. And I will say more about that in one of the subsequent lectures. Now, reaction order, therefore, is found empirically. So by clever experimentation, you can tease out that information, find out what those indices are, the M and the N, for example, in that particular form of the rate equation. And you can have fractional values, those indices as well. And that occurs mainly for reactions in the gas phase, for example, between hydrogen and chlorine. And you can also have negative indices. Yeah? So a rate law of this form, R equals rate constant times A to a negative index times B to a positive index. So the A to the negative M is 1 upon A to the N, right? That means that increasing the concentration of A will decrease the rate of the process. It will slow down the process. So that means that A acts here as an inhibitor of the process. All right. Another question there? Jordan? No? Go ahead. Okay. No, okay. I already mentioned reaction mechanisms. Reaction mechanisms really constitute a sequence of elementary steps that lead from the initial reactants to the final products. And you have to envision that the reaction mixture is composed of both the initial reactants and final products, but also contains the intermediate products that are formed in those additional steps, intermediate steps, right? So for example, if we consider the following gas phase reactions between hydrogen and chlorine, forming hydrogen chloride, this is not an elementary, this is not a one-step reaction, not a one-shot process, even though it is only bimolecular. So you might be thinking, well, that must be one of the elementary type, but it isn't. And that has to do with the complexity of the whole energy landscape for these processes. So the molecules follow a path of least resistance, so to speak. Sometimes that path doesn't exist, so there is a process that is intrinsically slow because of an energy barrier. that would constitute a bottleneck in the overall process. I will say more about that subsequently. All right, so the actual mechanism for this process has been unraveled and shown to consist of 3 elementary steps. One in which the chlorine molecule breaks up into atoms, which are free radicals. A subsequent step occurs when a free radical chlorine combines with a hydrogen molecule, forming the final product HCl, plus a free atom of hydrogen, which then combines with a radical chlorine to form the other product HCl. So that is how you end up with this stoichiometry. So you end up with 1 Cl2, 1 H2, and 2 HCls. And the intermediate H dot here cancels that, and this Cl dot cancels that. Now, there are 2 Cl dots here, 2 free radical Cls, which were produced here, but they're consumed in the rest of the mechanism. So overall, what happens is that you lose Cl2 and H2 and form HCl. So this is an example of a 3-step mechanism. And each step, of course, proceeds at a particular rate that is governed by a specific rate law for that step. Now, in many of these processes, there is what you call a rate determining step, a slowest process that basically holds up the production of the final products. It's like when you have a highway which at one point narrows into at a bridge, for example. So the overall rate of flow of traffic will then be governed by how fast the traffic moves across that narrow bridge. So that is the analog of a rate determining step in a reaction mechanism. So here we see an example, well, a generic example of an overall reaction. A plus 2B gives D plus E. In the first step, an A and a B combine to form an intermediate C plus final product E, which is presumably fast, and then another B reacts with the C just formed to form a D final product, which is a slow process. So it is this second step that will govern the overall rate of the reaction. A plus 2B gives D plus E. Right. Final slide for today is shown here. This is again a multi-step or 2-step process of a particular type, very important in enzyme kinetics, where the first step is a bimolecular process between 2 distinct molecules A and B, 2 different type molecules which form an intermediate product C, which then proceeds to react to the final product. Now, if that second step is very slow, so if C is converted to products at a very slow rate in comparison with the rate at which C is formed out of A and B, then C, since every reaction is in principle reversible, and that is the reason why we have chemical equilibrium in the first place, so we always have to consider the back reaction as well if it proceeds at a significant rate. Now, if this second process is very slow, then there is enough time for C to react back into A and B, because the conversion of C is being held up here. So there is an accumulation of C taking place due to the reaction of A and B. And as the concentration of C increases, the back reaction will go faster as well. And if this happens much faster than the forward reaction of C, then A, B, and C then momentarily reach a state of thermodynamic equilibrium, which we studied in the other part of the course, which is described in terms of an equilibrium constant. Of course, A, B, and C are continuously being used up in the process, so they're not constant in time, so it's not a true equilibrium, right? It is what we call a quasi-equilibrium that only exists because of the peculiar conditions of the process, because of the second step being very slow and thus being the rate determining step. Yeah, so we have a forward reaction constant for the reaction from A to B, of A to B to C, and a rate constant for reverse reaction. And the ratio of the two defines what we call the equilibrium constant. We can also write the equilibrium constant in terms of the momentary concentrations of A, B, and C, using the equilibrium condition that the forward rate, which is K forward times the product of concentrations of A and B, equals the K of the back reaction, which is written as the K reverse times the concentration of C. If you then reorganize that expression to make K forward over K reverse the subject, then that will be also equal to concentration of C divided by the concentration product of A and B. So this is another way of expressing the equilibrium constant. Yeah, so in this case, A, B, and C do vary in the course of time, but this combination of concentrations always has the same value. So if A and B decrease, C must decrease with them in such a way that this concentration C over concentration A times concentration B remains constant, equal to the equilibrium constant. So that means that we can write for the concentration of intermediate that it is equal to K, a constant, this one, times the product of the concentrations of A and B, right? So since the second step is rate determining, the overall rate of the reaction will be the rate of that second step, which is the concentration of C times the rate constant K. So this is the rate of the process, where the rate constant C or the intermediate concentration C can now be replaced using this form. It can be eliminated or replaced by K times A times B. If you do that, we formulate the rate of the reaction in terms of the rate of the second step, the rate constant of the second step, the equilibrium constant for the first step, and the concentrations of reactants A and B, which are the initial reactants. So what we have done, we have eliminated the concentration of the intermediate C in favor of an expression in terms of the concentrations of A and B, which is normally the desirable form of a rate expression, of a rate law. So we now have for the rate of the reaction that it is equal to a constant, which is a product of an actual rate constant times an equilibrium constant, which we lump together and call it K primed, which is like a pseudo rate constant, times the product of concentrations of A and B. And that rate we can then write as minus the rate of change of A or of B. Yeah, so that expresses the rate law in an acceptable format. And we can then proceed to try to solve mathematically. All right. So I think we have, okay, this starts lecture 2. That is for next week. All right, so if any questions come to mind in the course of the week, next week on Tuesday at 5, between 5 and 6, I will have consultation hour, so you can come with your questions prepared. All right, so that is, so I can see what I can do for you. Right, and I've also posted a PDF with the way in which this course is organized, the structure of the course, so you can read through that. So there shouldn't be any surprises. All right.
Sir, you